So I'm Karthik. I work in Minio as software engineer and primarily work around initiatives that has to do with Iceberg and also with AI. And in today's talk, so I'm going to walk through what are some of the important bottlenecks and important like factors that one needs to be aware. It could be architecturally, design wise, and the best practices um, to be able to write data to Apache Iceberg at massive scales. So here's how the flow of the talk would go. We'll start with some primitives on how committing data in Iceberg works, and then we'll go with some of the important bottlenecks or some of the key bottlenecks that one might first start to witness or come across as you scale your rights. After you pass a certain threshold, some of these bottlenecks starts to become more evident and start to pop up much more often, and then we'll go through what some of the best practices in order to scale your catalog, storage, and commits, and then we'll wrap up this talk. So let's begin with understanding some primitives about how committing data in Iceberg works. So Iceberg committing or committing transactions in Iceberg can be classified into a category of big data transactions. Now, we might have all heard about data transactions, the transactions that we often see in RDBMS or in relational databases, which are, of course, typically we classify into the bucket of data transactions. But big data transactions are a completely different mechanism. They follow a completely different mechanism compared to like the data transactions that we see in relational databases. So, firstly, big data transactions follow a transaction model or a conflict resolution model called optimistic concurrency, while as traditional databases they follow the model called pessimistic concurrency. So, what is optimistic concurrency? In optimistic concurrency, you can have multiple writers which write the data simultaneously into your tables, and while writing the data they don't have need any kind of a coordination, and they make an optimistic assumption that there is no conflict if they write data in parallel. And if they all write data in parallel, if they have no coordination, like what is how does optimism comes into play over here? The optimism comes into play only while writing the data, but while all of these like try to commit the data, the validation happen at the transaction commit time, and the transaction happens through the transaction commit API on your Iceberg catalog, and that's when a check that happens that where you compare with the base snapshot and try to see if there is any conflict. So unlike data transactions, in big data transaction you can have only one transaction that's performed at a time, and the next transaction needs to like typically rebase on the past transaction and need to retry. So, in typical data transactions, the clients are not very advanced. They can concurrently pass a lot of data, and the database server takes care of serializing them, ordering them, and performing the transactions. But unlike here, the clients have much more responsibility, and the clients need to ensure that they commit a particular snapshot of the transaction, and only one of them can be done at once. So, in short or in summary, like here is how the transaction in Iceberg works. So you read the current state of the table, and you will identify, or the clients will identify the table is at a snapshot n, and then you write all the Parquet files, and then you load the latest metadata, and then you apply all your updates, and you need to be sure that the snapshot what you are performing the transactions for, it's not already occupied by or all not already been performed by some other Iceberg client. So if it's been already taken, if the snapshot transaction is already performed, you'll see a conflict and you need to retry and rebase on the last snapshot. Now, as you scale your commits in an Iceberg table, as you like start to write more and more data, here are some of the bottlenecks that will start to uncover. Or these are some of the top bottlenecks that you might potentially encounter in the journey as you're scaling your Iceberg writes. The first one is the transaction API throughput, right? So, as I said, that in big data transactions or in Iceberg transactions or any transaction that follows the optimistic concurrency model, you can have only one transaction that performed at a time. So, which means that if you have a lot of concurrent transactions, let's assume that you have tens of Iceberg clients trying to commit or perform a transaction at the same time, only one of them will succeed. And the failed ones need to refresh, revalidate, and retry. And this is the rebase mechanism that I was talking about. And if this is not contained, all the failed writers will try to simultaneously retry at the same time, and this accumulates over a period of time, what we call it as a retry storm. And this queue grows faster and faster, building backlog of iceberg commits that needs to be done. And eventually, after multiple retries, they might stop trying altogether. Now, there are different kinds of transactions or different kinds of writes based on the nature of the workloads that you can witness on an iceberg table. So I think the ones that you often witness at massive scale are the append only writes, where you don't have any updates or deletes operations, like, or any of these need not be applied. Any kind of mutations on your data need not be applied. So these are typically your log data, your OTel style data, and these are the data that typically gets generated at massive scales, even at scales of few petabytes, like an hour, sometimes in large enterprises. And this is also potentially the easiest one to scale, and we will see how and why. And also, we have data where typically the CDC data, where or the change log capture data from transactional databases, where you have the updates, you deletes, and the merge, where you might have data mutations that needs to be applied on your iceberg table. Now, these kinds of writes are not so easy to scale. It's very hard to scale them independently, unlike append only writes, and the order of data writes also matter over here. So apart from the append only data writes, where you're continuously adding data to your iceberg tables, and also the updates and delete style writes, where you also try to mutate the data, we also have another category of transactions when we say like iceberg transactions, where it's not just about adding data, but there are also transactions which you perform, which are related to the table maintenance. So one such like very important housekeeping job is the compaction job. So you need to ensure that while you commit a compaction job, it should not conflict with your concurrent writes that is ongoing. So this needs to be separated from the rest of the data transaction that you perform on the table. So this need to be scheduled typically like once a day or twice a day, based on like how often you want to compact, and the volume of small data that you're accumulating. But don't try to do it in line. This needs to be scheduled as a different job altogether, and typically performed on partitions where you're not actively writing. So the gist of this section is that when we refer to iceberg transactions, it's not all the same. So you see different types of transactions, the append only transaction, and you can also potentially could refer to update or delete type transaction, or could be even maintenance job. For rest of the conversation, for rest of the talk, when we use iceberg transaction, or when we refer to iceberg transactions, we'll be mostly referring to the append only writes, where we have no data mutations, but typically just adding or appending more and more data to your table. And a classic example for append only data would be your application log data. So the second bottleneck, that is a key component which is not often spoken about, that becomes a very critical bottleneck for your iceberg pipeline, is your reliability of the catalog, right? So since most iceberg catalogs or iceberg rest catalogs that we see, catalogs like Polaris or Nessie, are built on top of transactional databases. For instance, like Polaris runs on top of Postgres. We can even see other popular implementations like Laykeeper, even it runs on Postgres. Now, while like you're operating iceberg pipelines at massive scales, you need to ensure that the DB doesn't fail over. If the database fails over, maybe because of huge volume of writes, or it could be something much more simpler issue, like the the drive is full, or the node goes down, or the drive where Postgres is running goes down, like all your writes will be blocked. So you might like think, hey, it shouldn't be like that the much of a hassle or a trouble to manage Postgres in production. But that might be true in case of more reliable public cloud environments. But in enterprise environments where mostly they're on prem, they're on their own data centers, these kind of environments are much less reliable compared to the public cloud environments. So you could often see like nodes going down, drives going down, maintenance job coming up. So your database failure can become a bottleneck for your entire pipeline. So the pool exhaustion could also potentially happen, which means if you have way too many clients trying to connect to your database at the same time, you can have some connection drop off, ultimately leading to commit failures. And as I mentioned, the catalog could even go down for different reasons. And I say catalog could go down, it could either be the database that's backing the catalog, or it could even be the catalog API that is built on top of the database, which may not be highly available. So you have this maintenance job where you not just have to ensure that the database that's the store or that's backing your catalog is up and running, but you need to also ensure that the catalog APIs are highly available and they're up and running all the time. And so it's, as I mentioned, this is something that's pretty less spoken about, but in enterprise environments especially, that we often see the cases where the catalog goes down and your entire iceberg pipeline comes down crumbling. So the let's focus our conversation on the up and only writes, like, which is the key topic which we're going to discuss on how we could scale up and only writes from few GBs per minute to even potentially writing petabytes of data. So the key consideration or the key component of how you should think or design your iceberg right is to separate two different components. So every iceberg client also writes data and also commits, right? So which means that if you spin off 10 concurrent iceberg writers, each one of them potentially could be writing its own parquet files, and they could also be like also committing the data at the same time. So the first key or first important idea or an architecture that needs to be considered to concurrently scale your iceberg writes is to separate the data committer with the parquet writer. So this is very, very important. Like, let's consider an example. Consider a Kafka queue where you have about, let's say, about 50 Kafka topics from which like you're continuously ingesting data and writing into your iceberg tables. And let's say that each topic consider has about 20 partitions. Now, if you have an iceberg client that is reading concurrently from each one of these partitions, and all of these iceberg clients are committing, there is a high chance that you might have these iceberg clients trying to perform a transaction at the same time, and they might conflict out. So in this case, where you have, let's say, 20 partitions in one Kafka topic, and you have 20 iceberg clients reading at the same time and committing at the same time, it's a very bad architecture, and this might lead to retry storms. So in this case, you need to ensure that the concurrent writers are not iceberg clients, but typically you separate out these two layers. Firstly, you need to like have parquet writers that read data from each one of these topics and partitions from these topics, and they can write the parquet data file continuously. So while the parquet data file is written, you can have a coordination queue where all the parquet metadata that's being sent into the queue, and then you can have a single committer service, which is reading all the Parquet metadata across these concurrent Parquet writers at the same time. And they could be like writing the metadata and then committing at a frequent interval. So this ensures that even though if you're linearly scaling the number of Parquet writers, you could go from 10 Parquet writers to 20 concurrent Parquet writers to 30, 40, and so on. You can keep scaling them linearly. And but since the committer is a single threaded system, and where it is like queuing up all the metadata and collecting them and committing at fixed intervals, like your committing pipeline doesn't grow linearly, though your data writing pipeline grows linearly. So this helps you to achieve the data throughput that you would need to scale your writes per minute, while not choking the iceberg pipeline by like trying to commit at the same time or trying to do too many commits at the same time, and this leading to like a retry hell or the retry storm. So so the next bottleneck potentially that comes like while you're trying to scale your iceberg writes is the bottleneck of your object storage itself, right? So this architecture, typically emphasizes on linearly being able to scale the parquet writes and disaggregate the parquet writes from the iceberg committing phase. So if you're linearly scaling the parquet writes, then potentially the workload on your underlying object storage, it keeps increasing, right? And for example, let's do a simple calculation. So if you're storing about 30 petabytes a month, you're ingesting about 30 petabytes a month on your iceberg table, you're potentially talking about approximately 40 terabytes of data that's being ingested every hour into your iceberg table, right? And in a lot of public cloud storage systems or in a lot of hosted cloud storage systems, the limitations are hit much faster than you often think. So you'll have stringent limitations around how many put requests that you could do within the prefix of your bucket. So this initially, like when you're not writing at this scale, these kind of limitations may not be evident, but this becomes like a serious bottleneck, something that you'll encounter right at the fence of scaling your iceberg writes. When you go from, let's say, uh, a 1 petabyte a month to 10 petabytes to 20 petabytes, at every stage where you're scaling up your writes, the volume of data that you write every hour, this becomes a serious bottleneck to be able to scale your data rights. And the second bottleneck that comes, as a result of the sustained pressure of workload on the object storage as you scale your writes, is the number of concurrent writers. So typically on S3 and many other cloud storage systems, the system throttles you under sustained load. So the system poses a serious bottleneck on how many concurrent writes that you could perform, and in turn, like becoming a serious bottleneck for the throughput of your writes. And the next one is the next limitation that you would potentially see is the egress cost that you will see at petabyte scale. So if you're like the network traffic is it's being metered in most public cloud environments. So typically, like as you see, not just you're limited on the throttling, because of the limitation on number of concurrent writes, and also like the limitation around how many put and get requests that you can perform. This is not just exclusive to just public cloud environments or services like S3. I think typically, this bottleneck, or performance consideration becomes very critical, even on like hosted private cloud object storages, like, and of course, like, I'm from Vinayo, and I can definitely be at a day-to-day basis. Like, we operate on deployments which are at few petabyte scale at extreme performances. And we could clearly see as the load, of the concurrent writes increases, how, it kind of back pressures on object storage performance, where the performance of the underlying object store becomes very, very critical. Um, and of course, like, so the TLDR, or the gist of this section of the talk, is that while your catalog can become an impedance at scale, because if your catalog goes down, your entire iceberg pipeline goes down. It's also quite important to know at the scales that we are talking about, the performance of the object storage also becomes a bottleneck. Okay, so yeah, I think that pretty much sums up some of the best practices that you need to be aware of, or one need to follow to be able to scale your append only iceberg writes. Potentially starting from few gigabytes to all the way go up to like few petabytes a month, and uh, please, like, scan the QR code. And recently, like, we if you want to know more about iceberg or best practices around ingesting data into iceberg, this is one of the chapters in the ebook that we released along with friends from Dremio. And for rest of the resources, feel free to reach out to us on Slack. Thank you.